Hey everyone, in this video we are going to talk about vectors. Alright, so the first question to answer is, what is a vector? Right? So a vector is something with a length and a direction. So these can exist in R2 or the plane, they can exist in three-dimensional space, they can exist in higher dimensional space. For us, we will mostly focus on the plane, so I'll often call that R2, right? But this is just like the XY plane is what you want to think of it as. And so there, in order to get a length and a direction, we often will write it as AB. And what this is saying, right, we have two coordinates here. And so it's telling you to move A in the X direction and then B in the Y direction. So a very simple example here. So let's let V be, say, 1, 2. And so if we start at the origin, which is where we'll usually start, then we would go over 1 to the right and then up 2, right? So this is 0.12. And so this would be our vector here, right? And it's this whole thing. It's not just the 0.12 where it ends up. It's really the length pointing in that direction, right? So this gives us a direction, and then how long is it? So we could write this. So the bars around it, this is the length of the vector v. And we know how to calculate this, right? So we can just use the distance formula. It's the distance from 0, 0 to 1, 2. And so here it would be the square root of 1 squared plus 2 squared, or the square root of 5, right? And that just comes from the distance formula. So one other thing to note here is that the vector does not have to emanate from the origin, right? I just said you go 1 in the X direction and 2 in the Y direction here. And so what I've drawn in blue here, right, these are all the same vector V, just starting from different places, right? So again, you're really thinking like coordinate free. It's a length and a direction. And so the 1, 2 tells me what I'm doing in terms of moving in a direction, right? Go 1 to the right, 2 up. I can figure out its length from that. But I could start anywhere. And so it's good to be flexible with where you are starting. But again, I will state that we usually will start from the origin if we're only dealing with like one vector. So we have two operations we can perform with vectors. So we can do addition. So here if u is, say, AB. So again, we'll mostly just focus on things in the plane. So that's why I have just two coordinates. And it's CD. Then u plus v is, well, what are you doing? You go A and then C in the X direction, so you just kind of add those up, and you go B and then D in the Y direction, so you add those up. And so you're just adding coordinate-wise, and so that's fairly simple, right? And then scalar multiplication, so first of all, what is a scalar? This basically just means a number for us, right? Like 5, pi, e over 2, whatever. These are just numbers. And so we can scale a vector. So if you have r is a scalar and, u is a vector, then r times u, or r times ab, is just you multiply by it in each of the coordinates. So ra times rb. But in the end, this doesn't really tell us a whole lot without pictures. So let's draw pictures of what's actually going on here, okay? Okay, so if we want to look at u plus v here, so first we've got u is 2, 1, and v here is 1, 3, right? And so when we add them, well, we just add them in the coordinates, right? So we should get 3, 4, but I want to think about how this actually works in practice, right? So if you do u first, right, so we travel on this blue arrow, and then instead of starting at the origin, we then do v, right? So like in that way, we are adding things, right? We first went 2 over and 1 up. And now we're going to go another 1 over and 3 up, right? So we have something that looks like this. And basically, this guy is parallel to the one on the left. And that is going to give us exactly what we want, right? So this is at the point 3, 4 here. And so the way you can view this is, if I just top this off, right, basically it doesn't matter which direction we did this, because addition of numbers. It doesn't matter in which order you add them. So you get this kind of parallelogram thing. And so the sum of the vectors is you just do this diagonal in the parallelogram. So this green guy is exactly u plus v. Okay? So that's how you should picture addition as happening in the plane. So then what about scalar multiplication? So here I'm going to let u be 1, 1. And so I just go to this point. And so then if I want to look at 3u, so I scale it. So if you scale by something greater than 1, you're going to be increasing the length, right? And so I am going all the way up here to 3, 3. So it's in the same direction, right? Same direction, but different length. And so you'll notice that all I did was change the length there, but again, that was because it was greater than 1. So what if I look at like 1/2 u? Well, that's going to be 1/2, 1/2, right? And so that would just be like this guy here. And so you can see the difference, right? That is going to shrink it. And so this is what scalar multiplication is doing. It's not changing the direction, but rather just the length. So for your first exercise, I'm going to give you these two vectors, so 1, 2, and negative 1, 3. And then, similar to what I just showed you, I want you to draw u, v, and then their sum. So I want to actually see the picture of that sum. And you should also compute it as well and make sure you're right. And then I want you to find the vector 2u plus 3v using your knowledge of scalar multiplication and addition, right? So you can do some mixture of them. And if you want, you can draw that on the picture as well. You just might have to make your y-axis a little bit longer there. So next I want to talk about vector valued functions. So this is something that takes in a real number and then it's going to spit out a vector. Okay, so you're going to start with a number and then you're going to get a vector. So a simple example is something you've seen before: cosine of t sine t given a t. So this is exactly tracing out the unit circle. It's what's called a parametrization of the unit circle, right? So anything, and the reason for this is that cosine squared plus sine squared is 1, right? So your x and y coordinates, when you add the squares of them together, you're on the unit circle here. And so what's really going on, right, is at f of 0, you spit out this vector, right? F of 0 is cosine of 0 sine of 0, so it's 1, 0. F of pi over 2 is going to give you cosine of pi over 2, or 0, sine of pi over 2, 1. Right? F of pi over 4 is going to give you root 2 over 2, root 2 over 2. And so that's this guy, and you can kind of see what's going on, right? So you're basically going around counterclockwise here, just like you would on the unit circle, and you're spitting out a vector that is exactly length 1 at every point. And it shouldn't surprise you that these are all called unit vectors, right? So a unit vector is just a vector of length 1, okay? And since we're on the unit circle, these are all unit vectors. And so the last thing to note here is this is the general form. So in general, it may not be cosine and sine, but the point is you're taking out one thing and then you can break it down into a function in each coordinate, right? So I write like f1 of t and f2 of t, where these are each functions themselves. So here, right, like f1 of t is cosine of t, so like your x coordinate is only taking in cosine and your y coordinate is only looking at sine. And this is very useful because it allows us to talk about things like derivatives and antiderivatives of these vector-valued functions. Right, so if I give you some vector-valued function here, what is its derivative? Well, again, what does the vector do? It's saying like f1 of t is what you're doing, your change in your x direction, and f2 of t is telling what you're doing in the y direction. And so if you're asking about the overall rate of change, it shouldn't surprise you after seeing multivariable and like partial derivatives that you just look at the rate of change in each direction. So this would be like f1 prime of t, f2 prime of t. And so let's go back to our example with cosine and sine to see how this actually works out. So here our derivative, right? Derivative of cosine is negative sine. Derivative of sine is cosine. And so let's just look at a few values, right? So f prime of 0, so again, when our angle is 0 or our time is 0 as we're going around the circle, is going to be, well, negative sine of 0 is 0, and then cosine of 0 is 1. And that makes sense, right? Because remember, what we're doing is we're going around counterclockwise, and so when we're at this point, we're traveling up, right? Straight up. And similarly, when we are at pi over 2, right, we should be traveling this way. So I should see something like negative 1, 0, because I'm going left instead of right, so negative in the x direction. And that's what I get, right? Sine of pi over 2 is 1, so I get negative 1, 0 here. And then maybe another example, again at pi over 4. So we get negative root 2 over 2, root 2 over 2. Which also makes sense, right? Like if we're here, we have a line of slope negative 1, and we're going counterclockwise, so we're going left there, but also up. And that's exactly what's reflected by this. So it kind of checks out and makes sense with the picture. And for your second exercise, I want you to look at this vector valued function t squared and try to draw it. If you can't see how to draw, I mean, you can just kind of plug in some t values and let that help guide you. But you can also find the derivative and realize that, like, as I change t by 1, I will change each of my x and y coordinates by what you get with the derivative. And so that can help you draw it as well. And I want you to see that that makes sense, that this f prime of t makes sense for what you see happening on your picture with regards to the changes in the x and y values. All right. Thank you for watching.